naught and T naught. And the initially enclosed volume in the cylinder is V naught. The gas then pushes on the piston to do work that is stored as potential energy somewhere far away. The gas pushes the piston an infinite distance and thus expands to infinite volume. The piston moves without friction and without leaking any gas. It is assumed that the continuum approximation remains valid for the gas. Okay, so it's perfectly insulated, so Q equals 0. There's no heat exchange. Okay. Q is 0, this is adiabatic, and it is also reversible because we says it was without friction and no leaking of gas. Okay, how much work in total has been done by the expanding gas? So this we can just use the formulas from the first part of the course. That's what we did. And in fact, this question is exactly out of the lecture. I talked about each and every point in the lecture. So how much work has been done? We can do this formula, work out, is 3 halves nR T naught times 1 minus L naught over L naught minus X. And all of this is the 2/3. And this is with X being in the compressive direction. So you should have had this on your sheet. If you didn't have this on the sheet, you could have, if you had the pressure, what you could have done is recognize that dW is equal to P dV, which is equal to P A dx, and then done an integral. Integrate dW is equal to P equal to A integral P of X dx, and then gotten work as a function of X, gotten this. But anyway, start with that. Al? Yes?
I understand why work has to end up being positive, while the work, but why, from a mathematical standpoint, wasn't dV equal to negative A dx based on the volume?
More time, why was it what?
So the volume is A times L naught minus X, correct?
Right.
So wouldn't dV be negative A dx?
Actually, that is a good point because of the way that we have defined X in this case. Actually, you would be right. So we could say X tilde and then do the, X tilde equals minus X substitution, which I think you did in a homework. So it says it expands an infinite distance. So how much work in total has been done by the expanding gas? So what we need to do is take the limit as x goes to minus infinity because of the way that we defined it, the work, which is 3 halves nR T naught times 1 minus L naught over L naught minus infinity, and all of this to the 2/3. Well, this minus a minus infinity makes us a plus infinity. L naught plus infinity is infinity. Something over infinity is 0. Well, that goes to 0. So we end up with the work total is equal to 3 halves nR T naught. That's the answer to part A. Now, so we might as well put A there. And B. B asks, what is the percentage of the initial thermal energy that remains in the gas after the expansion? So, by the first law, so Q minus work equals delta U, and this is 0. So we have U naught equal 3 halves nRT naught because it's a monatomic ideal gas. And we know that the final work here is 3 halves nRT naught. So we can substitute this in. And these cancel, and we end up with U final equals 0, which I said in class. So 0% remains. Part C, it asks for, in what way does this infinite expansion violate the third law of thermodynamics? Okay, the third law says that S equals 0 at T equals 0, okay? But what is the temperature after the infinite expansion? Well, we have to do the limit as x goes to minus infinity of the temperature. So that would be the limit as x goes to minus infinity of T naught times L naught over L naught minus infinity, basically, to the 2/3. So again, this becomes positive. This goes to 0. So T final is equal to 0. But this was isentropic expansion. And S naught was not equal to 0, so S final was not equal to 0. So we have S final not equal to 0, but T equal to 0. So that's the contradiction. Part D says, why does it violate the third law? That is, what is the main physical phenomenon that we are taking into account? And that is condensation and freezing, right? We said, oh, this is a gas, and it just stays as a gas all the way. But at some point, the temperature is going to get cold enough that it will condense and then it will freeze. And it's because of condensation. So the answer to part D is the gas will condense and freeze. And I mentioned this multiple times in lecture, that that's the issue. So what that lets you do then is you have a change in entropy with condensation and freezing, and that forces S to be 0 at T being 0.
Can that basically be summed up in saying that you're going to have intermolecular forces that will make your atoms basically bond more, which you're not taking into account?
Yes, because that's a very esoteric way of saying condensing and freezing, yes.
But you mentioned it's already ideal gas, right?
I did, right. And that's why I'm saying, why does this violate the third law, right? Because it does, it violates the third law, and this is the reason why. Because we're not taking into account the main physical phenomenon of condensing to a condensed phase. Let's go Ooh, yeah, that's what I said. Yeah. The temperature was 0. That's the thing. Third law has two parts. S is 0 at temperature being 0. We'll see. We'll grade you fair. All right. Question 2. Helium gas is continuously compressed in an axial flow compressor at steady state and steady flow. Okay. We draw a compressor, which is basically an inverse turbine. And we're compressing some gas, bringing some gas in, bringing some gas out. The compressor compresses the gas adiabatically and reversibly. So Q equals 0, no Q. Adiabatic and reversible, okay. When you see adiabatic and reversible, the lights go off in your head and you realize that means isentropic. This inlet, which is state 1, and the outlet state 2. Okay, the inlet temperature, T1, is 300 Kelvin, and the inlet pressure, that is atmospheric pressure. And the outlet state pressure, P2, is 18 times P1. Okay. You could go ahead and calculate that. It's not really necessary. Not right now. So, the kinetic and potential energies of the gas at the inlet are the same as those of the gas at the outlet. So what that means is delta KE equals 0, delta PE equals 0. So now we write the first law for open systems. It's steady state, steady flow, so we can use this form. Q minus WS equals delta H plus delta KE plus delta PE. We said that 0, we said that 0, we said that 0. All right. So that, we're going to be dealing with this. But part A asks, what is the outlet temperature T2? For this, you go to the fact that it's isentropic and it's a monatomic ideal gas. That's what helium is. And you know that from multiple homeworks and from looking at the periodic table of the elements. So, we have to use the formula, which would have been written down on your sheet. T2, T1 is equal to P2 over P1 times gamma minus 1 over gamma. Now, this you might have written down on your sheet. This equals 2 over 5, but if you didn't do that, maybe you wrote gamma equals Cp over Cv. Cp is equal to 5 halves R. Cv is equal to 3 halves R. Therefore, gamma is equal to 5 thirds. And then do gamma minus 1 and divide by gamma, and you get 2/5. And P2 over P1 is 18. So we have T2 is equal to T1 times 18 to the 2/5. And T1 is 300 Kelvin. So that's that. And this math, when you plug it in your calculator, is 3.1777. So then T2 is equal to 953 Kelvin. Plugging and chugging into the formula. B asks, what is the change in the molar specific enthalpy of the gas? What is H2 minus H1? Okay. So for this, we remember, as I told you to look at it, Cp equals dH dt at constant P. Now we did this in class too. We've used this formula a bit, which equals 5 halves R. And because it's a constant, in this particular case, we can see dH dt is equal to 5 halves R, which means that dH is equal to 5 halves R dt. So now we can do the integration between 1 and 2. dH is equal to 5 halves R integral of dt from T1 to T2, which means that delta H is equal to 5 halves times 8.314 joules per mole Kelvin times 953 Kelvin minus 300 Kelvin. And so then when we do 7 kilojoules. Part C. C is easy. How much molar specific heating or cooling of the gas occurs? Well, if you know what adiabatic and reversible means, Q is 0. That's all you had to write. Done. D. How much molar specific specific shaft working, W sub S is involved in running the compressor. Go back to our first law of balance, minus WS equals delta H. So WS equals minus delta H. So WS equals minus 13.57 kilojoules per mole. Sorry for that, per mole.
So why in this case you cannot use the integrate of the PEV? I think for the shaft work, I think from the lecture note, it's mentioned about like we can use I think from the people one, we have.
Oh, integral of VEP?
Yeah.
That should work, but I don't know that you, well, yeah, I guess you do, there is a formula, isn't there? V is a function of P, right? Kind of like this for an isentropic process. So it should come up the same, I believe. It may have been a math error in there, and we won't take off much points for math errors if you had the concept right.
How many points you take off if you forgot the kilo, like you just read your calculator wrong?
Nothing, I mean, small, we have to take something off because you're supposed to be engineers and pay attention, but it's small.
Okay.
The important thing is knowing what in the world's going on. All right. Question 3. This came from the lecture on when we were talking about entropy, and I talked about it in class, and if you'd read the textbook also, the section indicated on the second law of thermodynamics, it was in there as well. So even though it dealt with cycles, we already covered it, and in fact, the fact that you know what a cycle is now even better from the last lectures of this week means that's a leg up for you. This actually is super easy. It says, start with the second law of thermodynamics as expressed by the inequality for the change in entropy. So what is that? Delta S is greater than or equal to the integral from dq over T. Derive the inequality of Clausius, which expresses the second law for thermodynamic cycles. So for those of you who had the inequality of Clausius written on your sheet, this was super easy, but you could also just read it and figure it out. For a cycle, you end up at the same place. End state equals start state. So, since S is a state variable, delta S equals 0 for a cycle. So we have delta S equals 0, which is equal to this integral of dq over T, and because it's a cycle, put the little circle around the integral sign, and that is the inequality of Clausius. That's it. Put a 0 here and a circle there, and you're done.
President,
Question?
quickly before you move on to number 4. On
Yeah.
number 1, the work total formula, is the exponent to the 2/3 outside of the inner parentheses or the outer bracket? I have it had it written in the inner parentheses. It's the same answer either way, but
Yeah, and so we won't take off any points for that, whatever, yeah.
just for my future knowledge, do you know, is it?
Yeah, oh, let me look at the notes here. I may have copied it down wrong. Oh, yeah, you're right, that was the typo.
Okay, cool.
Yeah, it's supposed to be on the.
Got it, thank you.
And then part D, or part 4. Yeah. Now, part 4 was, I think, the hardest question. just from all the different steps that you had to do to solve it. So part 4 says, for the isobaric compression of a monatomic ideal gas from state 1 to state 2 in a closed system, start from the first law of thermodynamics and derive the relationship between pressure and specific volume and sketch it on a PV diagram, and derive the relationship between temperature and specific entropy, TNS, and sketch it on a TS diagram. So, let's go ahead and cylinder is going to be compressing. There is going to be cooling. And we're going from state 1 to state 2, so our initial values are T1, P1, V1. It's a closed system, so N is just N. Okay, and it says start with the first law of thermodynamics, so we write that on our sheet of paper. Okay. And then part A says derive the relationship between pressure and specific volume. Okay. Well, P is constant. And you could write work equals the integral of P dV, which then you bring the pressure out, and so you end up with V2 minus V1. You could write that. In fact, I wrote that first, and then I realized, well, okay, that doesn't really give me the answer that I'm looking for. What I need to just say is P is constant, and V decreases from V1 to V2. So V1 is greater than V2. And then we just sketch it. P and V, P is constant, so P1 equals P2. And we said V1 is greater than V2, so that means V1 is to the right and V2 is to the left. And we draw our dotted lines here so we can see what's going on. So that means that this is going to be state 1, and this is going to be state 2. Draw a line between them with an arrow. That's it. That's part A.
Spencer?
Yeah.
If I didn't write the sign, the arrow, is it okay? I just know like 1, 2.
Oh yeah. I know that 2 comes after 1. It's all good. Part B is a little more challenging. Derive the relationship between temperature and specific entropy and sketch it on a TS diagram. Okay. Well, let's do this. Delta S is greater than or equal to the integral of dq over T. That's second law. We can write that down. Some other things that we can write down. And we did this in class, and it was also in Olander. You have to know to start from this fundamental differential. dH is equal to TdS plus VdP. Okay? So we start from there. Because in this second law, it's got this inequality, and we don't really know what to plug in for Q. So you can't really actually start from here. It's too confusing. But you can start from here, and everything simplifies, as we will see. Here, P equals 0 because P is constant. Okay, good. So then what we can do is rearrange and say ds is equal to 1 over T dH. All right, very good. Now there's a number of ways you can proceed from here. You could go, H is equal to U plus dV, and use C sub V is equal to du dt, constant V, which is equal to 3 halves R. You could go that way, it's a little longer. The shorter way that I did it is more direct. We know that C sub P is equal to dH dt at constant P, which is equal to 5 halves R. And because it's a constant, in this case only, for monatomic ideal gases, this lets us say that dH dt is equal to 5 halves R, which then lets us substitute so that ds is equal to 1 over T times dH, which is going to be 5 halves of R dt. Now we've got T on the right-hand side, S on the left-hand side. We can do our integration. Integral from S1 to S2 of ds is equal to, we'll go ahead and pull the constants out, 5 halves R integral from T1 to T2 of 1 over T dt. So that means that S2 minus S1 is delta S, which is equal to 5 halves R natural log of T2 minus natural log of T1. And of course, by the property of logarithms, we can turn that into 5 halves R natural log of T2 over T1. So let's go ahead and keep on going. I'll keep it in terms of S2 minus S1. And then what I'm going to do is flip this on its head, 2 over 5R. And that is equal to natural log of T2 over T1. So then we do the exponent, e to the 2 over 5R times S2 minus S1 is equal to T2 over T1. So T1 times this exponent, 2 over 5R times S2 minus S1. And that is the relationship. So that when you plot it on a TS diagram, we know that the temperature is going to increase because we're compressing it. So we know that we're going to have to go from T1 to T2. And we know that and so we go from T1 and we're going to increase exponentially to state 2. And this is going to be S1, this is going to be S2. So there we go. All right. Okay. That is that. Yes.
I think one and two should be switched. When we have a smaller volume, I think maybe there's less to see.
Yeah, but we're heating it up.
Exactly, yeah. If the pressure is constant, then reheat is equal to
So let me just double check. Maybe I got it wrong. Maybe I need to dock myself some points. Well, anyway, that was what was in the lecture. So I will just quick double check that after a bit. Oh yeah, I can also use that answer as well. Just a moment. Solve this on the fly because I didn't memorize that. We could answer that question with S2 minus S1 is equal to C sub B natural log of T2 over T1 plus R natural log of V2 over T1. And then combine that and get our answer that way. I don't think I want to do that right now, but I can if necessary. Let me see if there's other questions first before we proceed. Other questions? Okay.
How were the questions weighted? Are they all just the same number of points? Is there-
I have not weighted them yet, to be honest. But, yeah, so this, let's see, this took, and I was writing it all out on the board and talking and the whole bit. That took 35 minutes-ish, and we had questions and interruptions. So, yeah, it was about the right length for y'all, because you were unfamiliar with the